Well, so we have already talked about the basic ideas of interference, right? Starting from the Maxwell's equation, then we talked about the superposition principle and what is the influence of the superposition principle on two waves. And basically, we got the physics behind the interference. And then we talked about coherent sources, the conditions of interference, and fringe pattern and all that stuff. And next we talked about one of the interferometers, which is our Fabry-Perot interferometer in the second lecture. And I skipped somewhat the mathematics, and then I talked about how the fringe pattern is observed, number one, and next how to analyze and make sense of the fringe pattern, right? So this is what we have done in the second lecture. Now in this third and last part, what I am going to show you is not only the left of the mathematics, which I have skipped. I will really take somewhat care to talk about it, but also I will show you how we make sense of this fringe pattern using the Fabry-Perot interferometer in our lab and use this to estimate something. And what is that something? That something is basically the measurement of the, number one, average wavelength of sodium. Number two, the difference between the sodium doublets. So this is very interesting, right? Of course, we are physics students, and in our practical class, along with theory, we must do something to show the importance of the theory. And that estimation, you will see, I will show you actual data taken by students, okay? And then you will see that indeed, from the data, when we analyze it, we indeed get results which agree with our knowledge. Okay, so now before I start, let me just again tell you, repeat somewhat what we have talked about. So basically what we are going to do or talk about is the Fabry-Perot interferometer, and it was first basically constructed by Charles Fabry and Alfred Perot in the late 1800s, such a long time, right? Now you see, as I have already told you, you can see this is our lab instrument, Fabry-Perot interferometer, and the heart of this interferometer is basically this mirror setup. So basically the device consists of two plain, parallel and highly reflecting surfaces separated by some distance, this distance, okay. Now what you are seeing here is basically two semi-silvered mirrors, right? And this form the reflecting boundary surfaces. So what is happening is that there is a sodium vapor lamp over here, and light from it enters not in the perpendicular direction but in the oblique angle. This I could have shown you if you have come in the lab. So the sodium vapor lamp is not placed somewhat over here but somewhat over this place or this place. It's an oblique angle, because you see, once the rays enter in the oblique angle, then there will be a reflection in case of oblique angle, you see, and this is what I have talked about. So this enclosed air gap basically generates ranges of from several millimeters to several centimeters when the apparatus is used interferometrically. Now here we will be talking about, say, millimeters, right? And basically we are having a resonant cavity, you can say. Now if the gap is fixed, then we call it a Fabry-Perot echelon. And if the gap can be mechanically varied by keeping, say, one mirror fixed, then moving the other one, then this instrument is known as interferometer. Okay, fine. So now what we are going to do, the main aim of this practical is to align this interferometer first, so that the first part is to make the two mirrors parallel. This I have talked about in the last lecture. Next, after setting the two mirrors parallel, you will see the fringe pattern. Then using the adjustment screws, the horizontal and vertical adjustment screws, then in the center of your vision you have to bring this fringe pattern, something like this, what you are seeing. And now today I will show you how using this we can estimate this average wavelength of the sodium light and also the difference between the sodium doublet. Okay, so let's start. Now the first part of this experiment, look what we are going to do. We are going to do an sort of, you can say, what? Wavelength measurement, right? Doublet separation measurement. So what sort of measurement is this? Length measurement. So basically, if someone asks you, what are you doing in this experiment? Fabry-Perot interferometer, one line. The answer is length measurement. That's it. Now, you know from our basic ideas that whenever we do some sort of measurement, we use a device, right? And now when you use a device or an instrument, you must first of all understand the least count of the device, right? So now what's the least count? Basically it's the smallest value that can be measured by the measuring instrument, right? Now our measuring values are only good up to the values of the least count. You can't measure something which has the value lower than least count, right? This is what we know. Okay, now I've just shown you some of the instruments. Say meter scale, what's the least count? Millimeter. Then vernier calipers, what's the least count? 10 to the power minus 4 meter. Then micrometer screw gauge, least count 10 to the power minus 6 meter. Now you will see in this lab, this particular instrument here, we have got a screw gauge whose least count is of the order of 10 to the power minus 7 meter. Let me show you. So the first part of this practical is the determination of the least count. Now you remember in the video I showed you this one. So this is the drum scale, and you see the pitch, screw pitch of the drum scale is 0.1 centimeter, and there are approximately 100 circular scale divisions. So this means the least count is 0.1 centimeter by 100, which is 10 to the power minus 5 meter. Here I'm talking in terms of meter. Next one is this slow motion screw scale. This is the one which you will be using to shift the fringe, which I have talked about and also showed you as well. Now for this slow motion scale, the screw pitch is 10 to the power minus 3 centimeter or 10 to the power minus 5 meters. Again, there are 100 circular scale divisions. So what does this mean? This means that the least count is 10 to the power minus 5 meter divided by 100, and this means the least count of the slow motion screw scale is 10 to the power minus 7 meter, and this is the least count of this device. Okay, good. Now let's see what we are going to measure. Well, you see, you know the sodium doublet, what's the wavelength? 5890, 5896 angstroms, right? So in terms of meter, it's approximately 6 into 10 to the power minus 7 meter. So if we have a device whose least count is of the order of 1 into 10 to the power minus 7 meter, then it's possible to really measure this average sodium wavelength. Good. But what about the sodium doublet difference? The difference is 6 angstrom. Now 6 angstrom, which means 10 to the power minus 10 meter. Now this is much lower than your least count. So how are we going to estimate? Now I am going to show you that we are going to estimate this using a technique and not measurement. The measurement will be done on the values of the order of this 10 to the power minus 7 meter, and the technique will enable us to measure this much smaller length. And this is one of the things you can take away from today, from this practical, that indeed it is possible using some particular technique to do a measurement of a physical quantity below the least count of the measuring instrument. Okay, so you must remember this. This is one of the takeaways from this particular Fabry-Perot practical. Okay, so now after the first part is the second part. And what's that? Basically determination of this average wavelength of the sodium light, which is 5890, 5896. What's the average in between, right? Now you see the sodium light, whose wavelength we will be determining, is allowed to fall on the glass plates P1 between P1 and P2. Now the inner surfaces of the glass plates are made exactly parallel. Again, remember this, when I am saying allowed to fall, it must fall in an oblique angle, not in the straight angle. You must remember this. In the lab I could have shown you. Anyway, so now you see, now, so once the two plates are parallel and the light falls in an oblique angle, then what will happen is that, I have talked about this in my last class, if the planes are not parallel, then you will see a large number of images. But once they are parallel, all the images will superimpose, and what will we see? We will see the fringe pattern. And this is the actual fringe pattern. This is what we see in the lab. Of course, to get this fringe pattern, we have to use the horizontal and the vertical screws to make this fringe pattern, make it to move it near the center of our field of observation. Now we have talked about this. Okay, so what's the next step? Next step is what I have skipped, is answer to this question: why and how these fringes? Why do we get this sort of fringes? And how do we get both? So let's start. So this is basically a very basic arrangement of the two plane mirror system. Now the rays are coming like this. So after this we have multiple reflections, right? So what's the path difference between beam 1 and beam 2 which are exiting? Let me first estimate. So the path difference is, you see, A1, A2 plus A2 into B. This is the path difference. Now again from this figure you can see that A2 into B is A2 into B is basically A1 A2 into cos of twice theta. This is theta and this is theta. So this is basically cos of twice theta. And you can break this down and you can get this result. So P, you will get A1 A2 into 2 cos square theta. Right. Now this is equation 1, this is equation 2. Next, so I can write the path difference P as 2d cos theta, where d is basically A1 A2 cos theta. You see, this is the d and this is basically A1 A2 into cos of theta. So this line cos theta. So basically I am talking in terms of the distance between the two mirrors or plates, whatever you can say, reflecting plates or semi-silvered mirror. Now, if the cavity has a medium of refractive index, n, then what will happen? Then the path difference between, remember, between consecutive reflective beams, it is basically 2nd cos theta. Okay, whereas I have told you, D is the plate separation, n is the index of refraction. Okay, and theta is the angle of incidence of the beam. Look into this picture. This is the angle of incidence, and I have been repeatedly telling you that theta must be positive. So if the beam falls on this beam like this, we will not see anything. So it must fall at an oblique angle, then only theta will be positive. Okay, now this factor 2 is due to the two reflections between the plates, and since all the multiple reflections come out parallel to each other here, we can use this to combine in a lens and observe this. Basically, in the lab, this lens is our eye, and this figure is formed inside our eye. Okay. Now, to start the mathematical analysis, let us assume that T and T prime are the amplitude transmission coefficients. Here T and here T prime, amplitude transmission coefficients at each of the glass plates. So what is happening here? Remember, I showed you in the last class. Do you remember? See, this is what we have talked about. So if the beam falls like this, then some light will go straight through and some light will reflect twice like this, and there will be even number of reflections between exiting. Remember? So now we are going to analyze this. Okay. So transmission and reflection, these are the two possibilities. So now I have talked about the amplitude transmission coefficients. So next I am going to talk about the reflection, amplitude reflection coefficient. Let it be R. Okay. Now this transmission coefficient is basically the fraction of the incident electric field that is transmitted, and the reflection coefficient is again the fraction of what has been reflected. Okay, now let's start with the actual expression. So let's see the expressions for the transmitted intensity of the emerging light beams, these ones. Let's see. Now here the convention is like this. N is equal to 1 defines a beam that travels right through the two glass plates. So this is N is equal to 1. So what will it be? E1. Here it is basically E0, you can say. So here you see E1 is equal to E0 into two transmissions T, T prime. So E0, T, T prime along with the omega, right? Next part, N is equal to 2. It defines a beam that is transmitted after being reflected. You see this one, E2. Now here you see the phase difference comes, this particular part. A1, A2 into A2B, which is the phase difference, so delta. And also you see there are two, what? T, T prime. So once it enters T and when it exits T prime, but there are two R. Why two R? This is one R, this is second R. So two reflections here and here, and again only two transmissions possible, enter and exit. So T, T prime. Next, let us consider the case of 3. How many reflections? 1, 2, 3, 4. So it will be R to the power 4. See here? But only again two transmissions coefficients, T, T prime and R to the power 4. So similarly, we can write the expression for the N case, that is N is equal to N, right? And remember, each time the phase is also taken into account. Okay, so here as I have been talking to you, E0 is basically amplitude of the incident electric field, and the exponential shows that the electric field is time dependent, and the delta is the phase difference between the adjacently transmitted beams. So now what's the total electric field? Let's just add all of them together. That's the total electric field, E total. And it is just, you see, a geometric progression series where A is this term and R prime is just this term. So the total transmitted electric field we can write like this. This is the transmitted case. Now you see the intensity of this transmitted electric field can be obtained by multiplying the transmitted electric field by its complex conjugate. So now I am talking about the intensity. So this is the one. Here, of course, I0 is the intensity of the incident electric field. Now, if we use this relation, cos delta 1 minus sine square delta by 2, and this fact, t prime plus r square is equal to 1. That means there is nothing else possible. You see, there is nothing else possible for this reflection and transmission coefficients. And so, if we use this, then our transmitted intensity becomes like this. As I have been telling you, this relation, you see, t prime plus r square is basically a statement. In a way, it is a statement of energy conservation, since it implies that there are no losses in the interferometer. Okay, now you see, we will introduce this 2r by 1 minus r square whole square. Let us take this term out and put it and give it a name, f. And this f is known as coefficient of finesse. And this basically, you see, it depends on the coefficient of reflection of the glass plates, r. Okay, so this is basically r square by r square whole square. Okay, now, good. So we have defined f. Next one. Next you see this thing. This intensity of transmitted beam, it varies as a function of delta. Varies with delta. So let's look into it. So now you see this phase delta is basically twice pi nd cos theta divided by lambda. And from this relation, for this transmitted intensity, you can easily find out the maximum and the minimum limits. And this is the maximum limit. Okay, and this is the minimum limit for these values of delta. And here I have shown you this transmission intensity plot. This is basically transmission plot as a function of this delta. Now what, not only as a function of delta, but also as a function of this reflection coefficient. So I have showing you the function as a values of r as well. You see what you are seeing, for small values of r, the peaks are quite broad. But as the value of r increases and approaches 1, you see, you get so much narrow peaks. And there lies the great significance. You remember in the last class, I told you when I was introducing this Fabry-Perot interferometer, I told you that it is used in communications, right? And let's see how this plot makes sense in this use of the Fabry-Perot interferometer during communication. You see, these peaks, they are slowly what? Getting narrower as the mirror reflectivity, and therefore the coefficient of finesse increases. Now, when the peaks are very narrow, then what? Then the light can be transmitted only if the plate separation d, refractive index and the wavelength, they satisfy this relation. Otherwise what? Otherwise, only this intensity will be transmitted only at this value and no other value. So this means otherwise no light is transmitted. You see, transmitted intensity is 0 here. This means no light is transmitted. No light is transmitted. And it is this property that permits the Fabry-Perot interferometer to act as a narrow band pass filter for a fixed D. Okay, so we have learnt why it is used as a narrow band pass filter. Okay, now you see the result of all these things, this thing basically, the complete interference pattern appears as a set of concentric rings like this. And the position of the rings, they satisfy this condition. Now let us, after all this discussion on the fringe pattern, we will now return to our discussion on the sodium doublet, which was our second part of the practical. Okay? And that is the determination of the wavelength, average wavelength. Remember. Now, suppose the initial separation between the mirror is D1, and if one counts the number of fringes, say maxima, appearing or disappearing at the center, you don't have to count anywhere else, at the center, which means what? Theta is approximately 0. Okay, then by varying the distance between the mirrors to D2, then what? You see, from D1 to D2, I have measured a large number of fringes. Then from here, we can get these two relations. This is the initial separation, this is the later separation, but they are all multiples of lambda, right? So from these two relation, I can get this value of lambda. Now by means of this micrometer screw of the Fabry-Perot interferometer, you see these D's can be measured very accurately, and counting the M with sufficient care, we can finally determine the average wavelength. Yes, this is what I was saying. That means this is now how we estimate the average wavelength. So basically you see, slowly I am moving the slow motion screw scale, and as a result the fringes will be shifted, right? See, this is how I am slowly changing the slow motion screw scale, right? And you see the fringes are being shifted, and we just count it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is how we measure this fringe shift. Okay, now this is actual experimental data. This is what I wanted to share with you. If you would have visited our lab, and if you would have the opportunity to do this practical, you could have done this measurement yourself. Now you see, the very first reading, first what we do is, basically we set the maze scale reading at a value, right? And then we slowly change the slow motion scale and observe this drum scale reading and slow motion scale reading. After counting the fringe shifted, number of shifted fringe for 20 times. So what we are doing is, we are taking each set of reading where each set corresponds to 20 fringe shifts. So first, when we start taking the measurements, that means no fringe shift, 0th measurement. This is the value 7303. Next, we keep on counting the fringe shifts by slowly moving the slow motion screw scale. You see, no change in drum scale, but slow motion screw scale has been changed from the reading has been changed from 03 to 77, and this corresponds to 20 fringe shifts. And this is how we keep on doing up to 300. So 16 sets of reading, each corresponding to 20 fringe shifts. And what do we get? This is what we get. So after this, what I am doing, you remember this formula here, lambda is equal to twice of d2 minus d1 divided by m2 minus m1. Now this is what I am doing. So this is the 0th reading and this is the 100th reading. So what I am doing, I am doing the subtraction. This minus this. That means m2 minus m1 is equal to 100. And again by doing the subtraction of these distances as well. And this gives me then overall this wavelength. Okay, now same. So this first reading corresponds to 100 minus 0. The next reading corresponds to 120 minus 20. After that 140 minus 40. After that 160 minus 60. So that this m2 minus m1 is equal to 100 condition is fulfilled. And this is the corresponding difference in distances. And then here I have done the average of these distances and then the mean value. And from there you see lambda is equal to 2d. This is the average value of the sodium wavelength. Now this is coming around 6000 angstrom. Bolo. So you see, this is the mean of these distances, right? This is the mean of these distances. Now you remember this formula over here, the mean of the distances, D2 minus D1. Next I have to divide by M2 minus M1, which is what? Which is 100, right? So this is the mean of the distances here, and dividing by the mean by M2 minus M1, which is 100. So you see 10 to the power minus 3, it goes to 10 to the power minus 5. This is what we have done. And then finally this lambda is equal to twice of D. This is what you get. Now this is set 1. In the actual experiment we take 3 data sets. So this is yet again another set, second set. Here the value is somewhat larger, 6180 angstrom. Now I have given you this third data set as a practice. You can do this yourself. So I am giving you this value and you can see how it is done from the previous case, and you can check yourself and find the value of average wavelength. Okay, so you can say this is sort of homework for you. Okay, so this completes the second part of our practical. Now what next? Of course the third part, okay, which is the doublet separation, and there we are going to talk about some technique. Okay, now so we want to measure the separation between the D1 D2 lines. Now you see this Fabry-Perot interferometer is properly adjusted for circular fringes for this measurement. Now in the intense region of the spectrum, in the center part here, the source of light emits, we know, two closely spaced wavelengths, lambda 1 and lambda 2, and each of them will have their own circular fringes. Now as we change the plate separation, what will happen? The combined fringe system will disappear and reappear periodically. Now this I have told you, I have shown you this thing in my last class. Remember this cycle by changing the distance between the two plates. Now this is what we are going to exploit for estimating the separation between D1 and D2. So this is what is happening here. Let me again show you in the video. The video I will show you later on. But let me first talk about consonance and dissonance. Now you see at the center here, the intensity is simultaneously maximum for lambda 1 as well as lambda 2 if this condition is satisfied, where n1 and n2 are the ordered numbers of the bright rings at the center due to lambda 1 and lambda 2 respectively. And of course 2d0 is the path difference between the two interference beams. Now under these conditions, the maximum of lambda 1 practically coincides with the maximum of lambda 2. Right? This is the scenario, like this you can say, both matching away. And the fringes are then said to be in consonance. The brightness contrast is very nice, and the field of view is distinct with maximum visibility, like this. Now of course there is another part as well, and that is when the separation between the plate is slowly moved away, then what will happen is that one maximum of lambda 1 might overlap with the minima of lambda 2, and this will happen when you say at a situation whenever the path difference 2d0 contains a whole number of wavelengths of lambda 1 and a whole number plus a multiple of half integer of lambda 2. That means one maximum and one's minimum. Then the bright fringes due to lambda 1 occurs at the same place at the dark fringe due to lambda 2. And what will happen? Uniform illumination in the field of view, and this is known as dissonance. Okay, now in the experiment we will be using this dissonance to our advantage because it is quite hard to understand this consonance. Let me show you in the video. See, I am now not slowly changing. I am now changing the plate separation quite fast. So this is uniform illumination, and slowly the consonance condition will come, but it will be very hard to identify. But the uniform illumination scenario is quite easy to understand. So we will be using this as our measurement. So this is what you are seeing consecutive consonance and dissonances as I am changing the plate separations. Okay, and this is experimental using our lab setup. Okay, so now let again move back to our theory. Okay, so after the video, you see this is the actual part where we are going to use this dissonance and estimate the doublet separation. So you see, for a particular dissonance position we have this condition. For the next dissonance position, after the plate has been shifted by distance d, okay, then we have got this condition, and from this subtraction, you see, just by doing some algebra, you will see we can get this value of lambda 1 minus lambda 2, which is approximately equal to lambda average square by 2d. Now I can estimate this movable distance, how much I have shifted, using the micrometer. So I can measure this, and this lambda average I already know from the second part of the practical, right? And see, this is yet another example. This is set 1, and in our experiment we do 10 sets of dissonances and take the measurements, and you see this is how we get the value of around quite close 6 angstrom. Bolo. Okay. So you see this n is basically due to this d change, so n number of lambda 1, and again here n plus 1 number of lambda 2. Okay, so you can say if lambda 1 corresponds, there are, say, what you can say, suppose 500th lambda 1, there are total number of 500 lambda 1 inside the cavity. It corresponds to 501 plus 501th corresponding to lambda 2, something like this. So n and n plus 1 here, and this is, you see, the result of 10 dissonance positions. We do the measurement, and you will be very amazed to know that indeed we can get the separation close to 6 angstrom. Okay, again this is another set for you to practice. You can practice it as a homework, and you can estimate the value of the doublet separation. Okay, and this is the final part of the practical, which is the last part, error calculation. So basically lambda is equal to 2d by n, and delta lambda by lambda is just delta d by d, and d is basically what? Amount of separation due to the n fringe shifts. So in the previous case, let me take just n is equal to 40, then d is this amount. And what is delta d? It is basically twice into least count of the slow motion scale. And so from here you see I am getting maximum percentage error of around 1%, less than just 1%. So this is our Fabry-Perot practical. Okay.